Today we are going to design a stable multivibrator using IC555. So go to Proteus, click here. This interface will open. Go to new project. Now this window will pop up. Name the project name AS. Let's suppose TTT. Next. Do not create a schematic. Create a schematic. Since we are creating a schematic, so remain it selected. Do not create PCB. If you want to create PCB, select one. We are not creating PCB, so remain it selected, this option. No firmware project. Since we are not using any microcontroller, so it is no firmware project. If you are using microcontroller in any project, then go to create firmware project. Since we are not using any microcontroller, so no firmware project. So this will be remain selected. So this interface will open. Go to this P component. Just type here 555 555 and then place it here. This. If you want to enlarge from here. Zoom it in this way. Now how to make the connection? See, this is the block diagram. Here we have already discussed VCC to this pin. This is VCC. A pin number 8 already written in there. So first VCC, let us connect a VCC power supply here. Reset, one more thing, this reset is active low. Whenever you want to reset the output, just press this reset, make it 0. It will reset the output. Since we do not want to reset the output, we will connect this reset to high. Whenever this reset is low, it can reset the output. We are connecting it. It is active low. We are connecting this to VCC. If there is 0, we are not providing 0 here. Whenever you provide 0, it will reset. So we are connecting it to VCC. We do not want to reset it in between. So just take the wire and connect both. You understand what reset means? It can reset the output. We are connecting, but it is active 0. We are connecting it to high. High means it will not reset the output. So go to this power supply, take a DC, place it here and connect it. One more thing, if it is multiple time, delete it. Just connect it from here. After connecting, right click on this and edit the value. You can name a suitable name. Suppose I am naming it as VCC. The voltage value is important, 5 volt. I am applying 5 volt here. Okay. So now this is completed. This part is completed. Now we have to place the resistor. This resistor and capacitor. This will be connected to a discharge and threshold and trigger to this point. Discharge at this point. Okay. The theory we have already discussed. So let us go to the component, take the resistor, select, just right click and rotate it. It will be easy to connect if you can rotate. Now these two resistors. Now these two resistors I have connected. Now this is connected to the power supply, VCC. I am connecting it here. Now this is to the capacitor. These resistors and external resistor and a capacitor. Take the capacitor, connect it, and now go to here and ground. The ground here, this is the IC ground, ground it. Now this part is completed. I will change the value, suitable value, register of the resistor later. First connect it here. See, this discharge, this is used to discharge the capacitor. Go and see this is to discharge the capacitor. When this capacitor discharge through this RV. When this transistor is on, theory I have already discussed, this capacitor discharge through this transistor. So this 7 pin discharge DC already it is written there. connect it to this. The capacitor will discharge through this. Now from here we will take output. 3 is Q, output, threshold and trigger both are connected to this capacitor value, capacitor voltage. Here to the capacitor, see here, threshold and trigger both are connected to the capacitor. This value changes when capacitor charges, this voltage increase. When discharges, this voltage increase. So this is this voltage. So we have connected this trigger and this threshold output to this capacitor. The reason we have already discussed, that as this voltage increases, this capacitor charges, this terminal voltage increases. If it increases, if it is greater than 2/3 VCC, output is 1. When output is 1, it resets the capacity, resets the SR flip flop. So we have theory, we have already discussed. Okay, coming here, so we have connected like this. Now this control voltage we are not using. This control voltage, the provision I have not shown in the internal architecture. It is used to change this terminal voltage, this decision point. This decision point by default it is 2/3 VCC, but there is a provision in the IC to change the decision point. That is, by default it is 2/3 VCC. So since we are not using it, we are not supposed to change it. So what we will do, we are not going to change this terminal voltage. The decision point is only by default is 2/3 VCC. We are not using this pin, so we will ground it. So we will ground it here, but instead of directly grounding, we will use a capacitor. We will ground it through a small value capacitor. We will ground it through a small value capacitor. So just connect a capacitor and ground it in this fashion. It's okay. Just change the value of the capacitor. Edit property, a small value, take 0.01 microfarad. 0.01 microfarad. Okay. Thus, this connection is completed. Now, yes, all the connections are made. At 3, we will connect the output. So go to the virtual instrument. Select the oscilloscope and place it here, and just connect the output at one of the channel A. I am connecting to channel A, one of the terminal of the oscilloscope. Now we have to calculate the value of this resistor. We are going to design for 75% duty cycle. So that calculation I have already made here. See, this I have already discussed. So this is the on time and this is the off. So T on is given as 0.69 RA plus RB into C. We have already derived and discussed this in the lecture. This is the charging time. During the on time, capacitor charges at it reaches to VTH, as it reaches to its charges, as it reaches to VTH, exceeds this. This is 2/3 VCC. This is 2/3 VCC. As this terminal capacitor voltage rises, as it tries to exceed 2/3 VCC, this terminal voltage is high. That means output becomes 1. Comparator output is 1. This because positive terminal non-inverting is high, so then it will becomes 1. This will reset.
This will reset the flip flop.
As it tries to exceed 2/3 VCC, this is the decision point. It resets. That means reset means it becomes 0. As it becomes 0, this becomes 1. This transistor is on. Now capacitor start discharging. This I have shown here. It start discharging. So all this is the on time. This is the off. Okay. See here, capacitor discharges through RB. So only RB is there in this formula. Duty cycle is on by off. So this comes out to be RA plus RB, RA plus 2RB. For 75% duty cycle, you have to calculate the value of RA and RB. We have taken one RA as 8 kilo ohm. Accordingly, I have calculated RB. RB comes out to be 4. I have selected RA as 8 kilo ohm. Accordingly, I have calculated RB 4 kilo ohm. So these are the values. Now, on period, T on. For T on here, T on 0.69, RA 8, RB 4 kilo ohm, 8 kilo ohm, 4 kilo ohm, C I have taken as 0.1 microfarad. C I have taken for 0.1 microfarad. So this comes out to be 0.82 millisecond. T of RB into 0.69 RB into C, it comes out to be RC, capacitor value I have taken as 0.1 microfarad. This comes out to be 0.27 millisecond. Okay, now let us come to the, after this calculation, go to here. Okay, now to change the value, this will edit properties, this I have to take as 8 kilo ohm. So I am just typing it as 8K. Okay, this I have to take as 4K. So edit properties, then make it 4K. Okay, this capacitor values I have selected as 0.1 microfarad. Okay, then put a point here, 0.1 microfarad. This all the values connections are made. The values of these external connections has been selected. Now go to the simulation and run the simulation. As you run the simulation, 1 minute, following output will come. As you run I'm just stopping it. As you run the simulation, if you are not getting the oscilloscope, go to debug and just digital oscilloscope. Here, to enlarge this interval, just for proper visibility, I am changing the time axis scale. Okay, now fine. Now just calculate to whether we are getting that calculated value or not. Get the cursor here. The time is, this time is on 3.29 millisecond, and this off time I am calculating. This is 1 second. This is 1 second. Here 3.26, 3.29. Okay, 3.30. Okay, 3.30. On time I am calculating. On time 3.30. This is the on. Just calculate one on interval 4.14. 4.14. Take the difference. If you take the difference, it comes out to be 0.84. Take the difference, this and this time, anyone, you can select anyone, on and this time, on or this time. Okay, I have calculated, it comes out to, this difference is 4. See here it is on 3.30, here it is around 4.14. So difference comes out to be 0.84. So on time 0.84, which we have already calculated in our calculation. Now off time, any interval. Here the time is 3.03, yes, 3.03, and this is 3.26. 3.03 minus 3.23, 3.03 minus 3.31. It comes out to be 0.28. You can subtract and verify yourself. 3.31 almost and 0.03 almost. Okay, so thus it comes out to be 0.28, which is almost the same as which we have calculated using the formula. So our design circuit is working properly. One more thing I would like to observe that this capacitor voltage, just plot it also. This will give you a better insight. This just calculate it, connect it to one of the probe. Just connect it. I am connecting it to B. Now run the simulation. If you are not finding the oscilloscope, go to debug, digital oscilloscope. See, the capacitor is charging. When output is high, capacitor is charging. When output is low, capacitor is discharging. The reason I have already discussed in the theory class. So in thus we have studied the Astable multivibrator using IC 555. We have designed an Astable multivibrator using IC 555. I would request you to design a Astable multivibrator for a 80% duty cycle. Okay, thus we can conclude the lecture. Thank you.